Hello, it's Keith here, and this is lesson 100 of the platform-specific series of the Z80 tutorials. Lesson 100, which means I've spent far too much of my life programming Z80 assembly, but I'm not done yet. And today we're looking at the Sega Master System, and we're adding hardware sprites to our previous tilemap example. Now, this is MaxTile, which is my multi-platform tilemap. It's software on some systems, hardware tilemap on others. This one's a hardware tilemap. However, the objects that are moving around were previously drawn with the tilemap, so they were simulated sprites, where now they're being made up of 8x8 pixel real physical hardware sprites on the Sega Master System. Now the Sega Master System has a limit of 64 sprites on screen and only 8 on a single line at a time, otherwise they start disappearing. The one interesting thing about the Master System is the sprites can be 8x8 pixels or 8x16 pixels, so double the height. The double height ones cause a bit of a problem with regards to the patterns, because the patterns have to be consecutive, which can be limiting, especially if you're using a large number of your tile patterns already for your background, which is a problem I had recently with another project I'm working on as an extension of this. I wanted to have a movable cursor and a lot of different designs for that cursor, and I actually ran out of tile patterns to do that with. So anyway, now what we're doing today is we're using the 8x8 pixel tiles, and we're actually changing them on the fly, because for things like the X and Y flip effect and also for the double height effect and things, we can't do those without large numbers of tile patterns, and we don't have really any left. So what we're doing is we're using the same 64 patterns for the 64 hardware sprites, and we're changing the bitmap to data that those patterns are drawing. So we're actually kind of using them like bitmaps in this case. So today's example code is much more like a system like the Amstrad CPC with a bitmap screen than it is with the normal tilemap thing, where we're just selecting a different pattern entry. We're actually redrawing the pattern each time. Now I'll just show you, if I go off the screen here, you'll see loads of extra stuff appear, and if I come back on, you'll see things disappear, and that's because of the hardware sprite limitations, either the line limitation or the on-screen count limitation. The MaxTile software that we're looking at today automatically counts, and as soon as it gets to sprite 64, it's like, by governor, we got none left, so we can't draw any more on the screen, and it will give up. So that's what we got, and that's the example we're looking at today. So let's go over to our code and let's check it out. So I'm running this with this example here, MaxTile Mid 2. Now the example file that actually does the code for the hardware sprites is this SMS MaxTile HSprite V2. Now this is V2 because V1 actually used individual tile patterns and didn't redefine them each time, but as I say, this means that we have very few hardware tile patterns left, and so if we're predefining them all in advance, well, we have to predefine the double height ones, and the solid fill ones, they may never be used, so possibly not appropriate, and especially not if you're doing something super tricky, which I am with my new Reiko game engine, which I'm working on, which uses animated video backgrounds, which uses every single tile pattern available on the system. So there's nothing left for hardware sprites really. So this is the kind of thing you may want to do. Anyway, so that's what we're going to be looking at today, and we're going to be looking over the code of this. So firstly, our pattern data. Well, our pattern data is actually, it's 4-color pattern data like before, and of course it's in the classic Master System format, but we're only defining 2 of the bit planes. You can see them here, and we've actually aligned them in the exact same way as we have with the Amstrad CPC and those kind of systems. Before, we were loading the tile pattern data into VRAM at the start of our program and then just selecting those patterns as required by the screen, but this time for the sprites we're actually drawing them on the fly, and so they need to be at the correct memory locations for the specified tile numbers that we're going to draw into the hardware sprites. So that's how that is working. Let's go over to our example here, HSprite V2, and let's see what this actually does. Now, if you remember before, we had our previous example, which was using the hardware tilemap, and this was selecting a VRAM destination within that hardware tilemap to change the pattern that's being shown. This one works completely differently. Now we're actually taking the BC location, which is in pairs of pixels, logical units as I call them in my tutorials. Logical units are always pairs of pixels in my tutorials these days. And so we're converting that to a pixel location, which we're going to need for the actual locating of the sprite. You'll notice there's a H on the end of these because this is designed to work in tandem with the regular MaxTile for the background. So we have to use different names for the code to work. Now, apart from that, yeah, the initialization all works kind of similar to the way before. As I said last time, these routines, draw tile H and draw tile originally, are only executed if the update bit was set, and that will have been pushed out of the accumulator as this program was run. And so when we do this shift left accumulator here, we're actually pushing a 0 in to clear that update flag effectively. BC is the source tile map, which defines the layout of the tile patterns for either the sprite object or the background itself. So that's what this is doing, and this is basically the same as before, and this is pretty similar to before as well. We're selecting this time the bitmap source offset data here. Now last time in the hardware sprite example, we were shifting this to be a tile number, and then we were moving that tile number into the VRAM of the tile map. But this time we're actually setting the pattern data of one of the hardware sprites. Now, before we can start playing with hardware sprites, we need to work out which one we're going to be using. Now, H sprite number is the key to this. This is an entry in memory, a single byte, and this will start at 0 at the start of a frame, and then as we use sprites, it will go up. If it's got to 64, though, we've run out of hardware sprites, and so we certainly don't want to draw anything else on the screen because we've got nothing else to draw it with. So in that case, we're going to give up, and that's what jumping to this does. Of course, if we get past this, though, we've actually got a hardware sprite to use. So what we're doing here is we are taking the 2 bytes of this source tile map, and that is now the pattern number. As I said last time, in case you didn't see it, these are designed to be pre-multiplied by 16. These bottom 4 bits have other purposes. So the tile number is effectively multiplied by 16, and that's because this code was designed to work with 4 colors with an 8x8 tile. 4 colors, 8x8 tile, that is 16 bytes. So our patterns are 16 bytes each. So by sorting out our memory like this, we've effectively multiplied the tile number by 16, and we can just add it to the DE source memory address, and that's the pointer to the start of our tile patterns. Okay, so that's got our source address that we're going to use for reading our data. What we need to do now is we need to select the VRAM destination of the pattern that we're going to use for this hardware sprite number. And that's what this routine here does, get sprite pattern address. Let's check it out. So here is get sprite pattern address, and what this is doing is it's loading the hardware sprite number. Now we're starting from hardware sprite number 128, which is at memory address 3000 in VRAM, and that's basically allocating pretty much the maximum amount of memory we can for tile patterns, and that's for next week's example where we're going to use a simulated bitmap screen which needs 384 tile patterns. So that's why we're doing that here. What we're then doing is effectively multiplying that number by 32, because each 16 color pattern will require 32 bytes, and so the pattern number times 32 is the memory offset for the pattern we want to change. Now our source patterns are only 4 color. We're going to convert them to 16, and we're going to actually do it in a little bit of an odd way, and that's for compatibility with the bitmap example next time. We'll see that in just a moment though. But basically we're calculating our VRAM destination here, and we're adding that to 20. We've actually effectively adding it to 30 here because of that adding 128 there, but and then the 40 here is defining this as a writing address. I guess I could change this actually. I could take that 120 out, I think, and I could change this to 30, and that would actually have the same effect. Yep, everything still seems to work fine, so maybe we've saved a couple of bytes there. So I was looking for small savings in these pieces of code I plan to reuse, so there we go. So we saved a little bit of memory there. But that's calculating the pattern address for the bitmap data of this this sprite's pattern. And it's selecting it so that any writes we do now will be to the correct pattern. So if we go back to the start of our code here, and we just see the code that follows on from that. So we've now selected our VRAM destination here for the pattern data. So all we need to do now is we need to take that pattern data that we calculated here, and we need to write it into VRAM. Now we've got 2 bytes per line, but we need 4 to write into memory. And logic might say that we're going to use bit plane 0 and 1 as the ones that we've got, and maybe use zeros for 2 and 3, or some predefined palette offset. But actually what I'm going to do is I'm going to use zeros for the first 2, 0 and 1, bit plane 0 and 1. And then I'm going to use the source data that we've got in our source pattern for bit planes 2 and 3. And I notice actually we might need an extra delay here. Loading A with 0 won't actually be long enough. We might need a couple of no-ups in there. If we were running on real hardware, the emulator doesn't accurately emulate the VDP's maximum speed on the SMS. But we'll leave it as it is for now. But as I say, just to notice that a push IX and a pop IX is about the minimum that we need for a between writes to the VDP. Anyway, the reason I'm setting bit planes 0 and 1 to 0 here and using bit planes 2 and 3 for our graphical data is for compatibility with next time's example, which is the simulated bitmap screen. We're doing some tricky things with the two palettes for the background tile map so that we can use each tile twice and simulate a 256 by 192 4-color screen. That has a knock-on effect to the hardware sprites, which always use the second palette though, and so for compatibility with that, I'm setting these 2-bit planes to 0. If you set these to 255, you can actually solid fill the background color in black if you want. I've got it set to transparent here, but that is something you can do if that's what you want. Anyway, so this is writing a single line of our destination pattern. We're using B as the counter for the number of lines, so 8, and we're just repeating until we've done the entire pattern for this hardware sprite. So this hardware sprite now has a graphic. What we now need to do is we need to give it a position and get it on the screen, and that's what this create sprite tile does. Okay, so here it is, and so what this is going to do is it's going to set the X, Y, and pattern number for this this sprite on the screen. So basically there's a couple of memory addresses we need to use here. There's 3 bytes for each sprite. The first byte is at memory address 3F00 onwards, and there's 1 byte per sprite in ascending order. And so we're taking our hardware sprite number here and selecting that as the bottom byte of the address with 3F as the top byte. So that will be 3F00 for sprite 0, 3F01 and 3F202 and so on. And that's actually the Y position, which we've got in L here. So we're writing the Y position there. Now the next 2 bytes are the X position and then the tile number. And those are a pair. And these start from 3F80 onwards, and each neighboring 2 bytes are the X position and the tile number. And so we effectively need to double our hardware sprite number and then add 80 in hexadecimal, and that with 3F as the top byte will be our VRAM destination. We then write the X position and then we write the tile number here. We're adding 128 because our tile patterns start from 3000 in VRAM. Now, just a sort of thing to point out here is there is no XFlip option on hardware sprites. So if you want to XFlip a sprite, you either need to flip the data like we're doing here, or have a second copy of all the patterns you might want to use. Entirely up to you, but there is no XFlip on the sprites, just on the background tile map. So yeah, there is limitations there. It'd be nice if we had XFlip, but it's just nice we have hardware sprites, to be honest. So we can't really expect everything. Anyway, that's the most basic version of our tile drawing routine. Now, exactly the same as last time. The whole point of MaxTile is it works the same on every system in every way. And so when we're using hardware sprites, we have all of the same options we had before with regards to XFlip and YFlip and double height and solid fill and so on. And so what we're doing here is we're checking to see if we've got an XFlip or YFlip. If we haven't, but we were using an advanced program, and the advanced program was being tested as bit 0 here, but it was originally bit 1 before that that update bit was shifted out. So bit 1 is the program, which defines the advanced programs. And so if both of the XFlip and YFlip are 0, then it's some kind of special custom code, that's double height or solid fill, things like that. Otherwise, we're doing some kind of flipping. Here we're clearing the update flag here, and we're doing it in a slightly different way because of this branch over here and this masking here, but we're clearing the update flag here, and then what we're doing here is we're calculating the source pattern data in HL as before. Now what we then need to do is decide what kind of flip we're doing. Are we doing some kind of Y flip, or are we just doing an X flip? If we get here and we're not doing a Y flip, we are just doing an X flip. Now, how does XFlip work? Well, exactly the same as on the bitmap systems. Actually, we have a lookup table. We've got this flip lookup table. If we go to our source program here at the start somewhere, in our original program code, in our main program, we defined a 256-byte flip lookup table. Now, it's important that the bottom byte of this memory address is 00, because basically the 256 bytes, the address of the bottom byte is the source that we want to flip, and the data at that address will be the flipped equivalent, and that's how we use it. So what we're doing here is we're filling our lookup table, and we take H and L as our memory address that we're going to write to, and the L byte becomes the source that we want to flip. And then we're just shifting all the bits out of A into B, and then writing B into the lookup table and repeating all 256 times. And so that lookup table contains every possible conversion of our source data. So when we want to use it, all we do is we load B with the top byte of the lookup table address. We load C with the byte that we want to flip, our source byte. We then read in from BC, and that then gets us the flipped equivalent of the byte that we loaded into C, and then we're just writing that to VRAM in the exact same way as before. So here again, the first 2-bit plane just contains 0, and then the next two contain the X-flipped data. So that's how we do our X flip. Now we've got our Y flip code here, and our Y flip code first checks if we're also X flipping, because in that case we're X and Y flipping. Y flipping, very straightforward. We don't use a lookup table. We just move backwards through our source data. We write in ascending order to the destination. We read in backwards. So here we're moving 14 bytes to the last line of our pattern data. And so again, we're doing 8 lines, and then we do zeros for our first 2-bit planes, and then we read in 2 bytes here for the 2-bit planes of the last line of our source, the first line of our destination. And then after we've written the line, we move back to the first bit plane and then back a full line, so we can do the exact same thing for the next line. We repeat 8 times, and that's Y flipped our sprite, very straightforward. And then the final one is XY flip, and XY flip just uses both tricks at the same time. So we move to the last entry in our source data, and we X flip it all with the BC X flip lookup table. So we've X flipped and Y flipped there. Again, in all cases, we're just doing this effectively setting the bitmap data of the sprite. The sprite bitmap destination has been correctly selected by this routine, and the actual defining of the location of the sprite is done by this routine here. And I think actually I could probably optimize this up a bit by changing this branch to jump up here and things. It's functional, but it could do with some tidying up. I don't have a lot of time to make these tutorials, so sometimes they aren't as optimized as I like, and I do tend to, if I keep using them, go back and poke them a few times and make them a little bit better later on. But it does work definitely anyway. So that's the X flip and the Y flip and that kind of thing. The remaining ones are the custom types of tile. So these are basically double height, fill, and then transparent. Now, ironically, all of our sprites are transparent anyway, but we have to maintain compatibility with the other systems, so we have to have the functionality here, even if it doesn't necessarily do so much. Now, custom uses an extra 2 bits, and so this leaves us with just 10 bits for our tile number. What was previously the L byte becomes the top 2 bits of the address, so we're going to shift that over here. So those are the 2 top bits, and then the second byte of our source pattern becomes the bottom byte of the tile number, and how we use that depends on what kind of graphics we're doing, and that is defined basically by the what were the least significant 2 bits of the tile number before, but they are now the program command. So the one kind of program is the double height. Now this effectively we use the source pattern data. We only use 8 bytes of it this time rather than 16 because we're doing each line twice. This was intended to save memory, but it kind of gives a stretched effect, which maybe you think is fun. You know, a bit like the Metal Slug games used to do the stretching effect quite a lot because that was something that the Neo Geo was very good at. So yeah, there may be times you want to do it for a special effect or something, but that's not. It was designed to save memory anyway. So what we're doing here is basically we're just sending each line of our source pattern data to VRAM, but then we send it a second time, and our loop count this time is just 4 because we've sent each one twice here. So I mean, you'll notice there's a slight difference here. We are moving back up a line here, and then we are basically moving down a line here just so that we are jumping back and showing the same data twice. But I say that's how we are doing the double height effect. We've then got the fill effect, which basically uses a single pair of bytes for each line and repeats those 4 bytes, those 2 lines, basically for the entire graphic here. So that's the fill effect. And then the final one is the transparent sprite type. Now this has 2 purposes. Our box-shaped graphic sometimes has unused parts, like around the feet there's actually no tile there, and that is defined by a 255 tile, but anything else is usually transparent. But in the case of this system, well, actually all of the sprites are transparent anyway, so we're just using the regular drawing routine, correctly selecting the VRAM, the source pattern data though, because of, we're doing the multiplication different because the memory layout of the source data is slightly different in the tile map in that case, because as I say, the least significant 2 bits of the tile number, what were the tile number, is now the command bits. But say basically that's pretty much the same, because I say all of the sprites are transparent in the way I'm using it here. The only final thing that we need to discuss though is the removal of unused sprites, because as things go on and off the screen, If the number of used hardware sprites goes down, we actually need to remove some of the objects from the screen, otherwise we'll leave clutter and of old sprites. And so all we need to do that is give any spare sprites, so anything that's, if we've not used a full 64 sprites after we've drawn our frame, basically all we need to do is do something with the sprite that's going to get it off the screen. And here we're setting the YPOS to 200 here, which is off the screen, and so that sprite won't be shown. So that's how we're hiding the unused sprites, and that's just the last thing we do have to do for this example. So there we go. As always, let's say go to my website and download source codes and the build scripts. That is the example, and that is the code that handles the hardware sprite settings. And as I would say though, if this example was too complicated for you, I would totally understand that. But please, take a look at it and try it out, and maybe you can use a few parts of it, even if the overall code is a little bit too complex for you as a beginner. I would totally understand that. And I'd always suggest, if you are looking to write things, and you can do so, I'd always suggest you write your own project, you write your own code that you rely on anyway, because then you'll completely understand what it does. You won't have bits that you don't quite know how they're working, and they'll do exactly what you want, and no more and no less, and you'll probably save some memory as well. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.